All right, this is part 2 of the coding session to get Bose-Einstein condensate and look at what happens to phonons when you print them on a moving system. We looked at a 1D system. We saw we could imprint a phonon with a slight potential deviation, and then we saw that phonon oscillates. Now, there's a couple things that we didn't do here. One of the things is we didn't actually minimize the energy. That may be important or maybe not. The initial state that we started from here is the Thomas Fermi state. So we might want to minimize. So let me just show you how to do that. So you can import from gpe.minimize something called minimize state. Import. So from GPE import minimize state. I want to split this cell. I'll do this in a new cell here. So there's our Thomas Fermi state. Okay, so this is a class. This is an interesting point. It seems like I didn't install the correct version of MMF utils. That's probably, maybe that's true. Let's see if we can do that. PyTime ODE might not have needed the new version of MMF utils, so it might not have installed the new version. Let's just see if we can do this here. So open a terminal. See if this pulls in a new version or not. Yeah, it's not pulling in a new version. Okay, so we probably need to install a new version of MMF utils. So we should pull that from the repository. So this is a package level thing. So I'm going to go into that repository directory. And I will hg clone again. I'm going to log in with my SSH so that I can do this with the SSH version of it. You can do it with the HTTPS as well. So let me open a terminal here. Oh, no, that doesn't help. Okay. Okay, and the command that you want to do is hg clone https / your username at bitbucket.org/mforb/mmf utils. MMF utils. Okay, has everyone had a chance to do that? Okay, so then once you've done that, cd into the MMF utils directory. Let's look at the branches. There's only one. We're at the top of this, and let me just check the log messages. Oh, actually, we should clone my fork. Okay, so I cloned the wrong one. So what okay, you could delete it or you can actually pull. So what you can do is you can do this. You can go hg pull, the same command you did before. Oh, I don't know why it does that. Anyway, so you can do hg pull http. Well, actually, let's do it a different way. So go into the .hg directory. Look at a file called hgrc. Oh, I'm apologizing. I think I did this on your computer by mistake, your account, because I'm working on yours. Okay, that's okay. I'm going to present with yours. So what you see is that the default is https colon your username at Bitbucket. That's where you cloned from. Now we actually want to get it from the fork, which has more up-to-date stuff. So I'm going to do that. That changes the default location. This is important to know. If you have a project, you can push and pull from multiple different repositories. Like you might want to push and pull from a cluster or from Sage Math Cloud or from your desktop or from something like that. You can put different paths in here. So this is the default one, but you could call one called SMC and then that point it somewhere else, or the cluster Kamiak. So you can add whichever, as many different sources in here as you want. I'm just changing this one to MMFutils fork. Okay. Now you can go hg, go back to the top level directory, and you can go hg pull, and this will pull everything from the fork repository instead of from the one that we had. Now to just check this out, you can do in, which will show you what's coming in. You see that there are a whole bunch of changes that are coming in, and in particular enhancements related to Broiden, and that's what we need. Okay, so you guys need to update MMFutils if you don't have it. We're doing this in the top level repositories directory, and so we cloned it from Bitbucket, and you want to clone from MMFutils-fork. Okay, so then you can pull this. Oh, the top level is of your project. No, that's one level below. The top level is in repositories. Okay, so anyway, and then you want to update. So I'm doing this for Sage Math Cloud. So then we update. Now we're at the top, and then hopefully now if you go and you run that, you won't get an error. Let me do this in my example for just a second, and I'll show Ryan where it is. And then the final thing that you want to do is you want to pip install this. Pip uninstall MMFutils. That'll get rid of the one that came in before. And then you want to install this one. And since this is from a repository right here, we'll do this with -e, so that if you edit the files here, then, okay. So you guys clear what to do? Go to the top level repositories directory, and then hg clone. Are you doing it on Sage Math Cloud? Oh, okay. So then you'll need to go somewhere wherever you clone, like your work Bitbucket MMFBB folder, and get MMFutils. Then go to the top level repositories directory. Now, Ryan, you said you don't have, so you have to put this repository MMFutils somewhere on your computer so you can install it. Pick wherever you want that to be. So I have a work MMFBB, and that's where mine go. Found it? No, this is global for the project. Yeah. And then clone the MMFutils-fork. and then update. Okay, so once that's done, then we'll go back to the example ring, and I will see if this works now. So we'll restart everything. Now why is this not still working? Um, ah, so there's a couple other heads. So Septar, well, everyone, I'll let me know when you're ready. So do you have the MMF utils in there? Slash MMF utils dash fork. And you can clone it to a directory called MMF utils. Okay. Okay. Sure. And you want to uninstall it too. So pip uninstall MMF utils. That'll get rid of the one that we installed earlier. Where are you guys at? Okay. And then go into the directory and go pip install, and you might want to go install -e MMF utils. Oh, sorry. Before you do that, go into the MMF utils folder. Do an hg log -L5 or 10 or so. So the latest version is 134. You see that? What do you see on there if you do hg log -L5? That limits to 5 log messages. So you should see the revisions. What do you mean nothing? Are you in the MMF utils folder that you cloned? $134? Okay. See, so what? Did you clone it from the fork? Okay, so we want this 134. Now, it's not the default branch. So if you go HG up, it won't necessarily go there. You have to be specific. You want to go to 134, HG up -R134. 134 is not unique, just so you guys know this. That's the number in your particular repository right there, but the unique numbers are the hashes, those long numbers after it. So 134 on one machine might not be 134 on another machine. If you just cloned it, it will be, but okay, makes sense? So it's a shortcut. Now pip install -e dot. Done? Okay. I will at some point, once I'm finished testing that, I'll push that to the main one, and then you just pip install it. It'll be fine. But for now, that's what you have to do. All right, so now we go over here. We restart the kernel. And we will run. Now, hopefully now we can import the minimized state. Okay, good. So now the way minimized state works, you give it a state, and then you can either fix the particle number or you fix the chemical potential. So you create an instance of this, your state, and then you run minimize. But we didn't actually minimize the state. The initial state that we were working with was actually the Thomas Fermi state. So I want to see if minimizing makes a difference. Okay, so we should be able to just run the minimizer. There we go. We get a new state. That's what we'll call S now. Yes, it should do it at t equals 0. We can plot it. And it looks very similar to what we had before, right? Did we plot the one before? Let's plot the one before just to make sure. I've called the new state S1, so we have the old one too. So they look very similar. We can try and see if they're exactly the same by computing the difference. States act like arrays, so you can actually subtract them. Oh, S, right, thanks. And so you see there is a change at 0.02 or so from minimizing, not too much, okay? One case where it would be quite a big difference is if we made the healing length very large. So what if we made the healing length, instead of 1 micron, let's make the healing length, I don't know, 5 microns. And so we'll divide this by 5. Okay. So here's our Thomas Fermi initial state. The amplitude is now even too large. And then when we minimize this, the healing length is really quite large. So there's quite a big difference between the two. Okay? Yep. Anyway, I'm going to go back. Let's not do that. Let's leave it where we had before. But yeah, we're going to do something new now. Okay? All right. So let's copy this class. Well, actually, it's kind of useful to have everything. So let's copy everything into the 2D section so we can start fresh. Okay, so everything is more or less the same here, but the big difference is we now have to properly code in a, well, no, a circular potential. Okay, so instead now our potential is going to be, so let's see, so it's 2D. To do is we need to have a radially trapping potential, okay, and then we'll have to put this cosine modulation radially, okay? So we probably want to work in polar coordinates. So let's do x and y. Then r is equal to, well, let's do r2, which is x squared plus y squared, right? And then theta, we might want, which is np dot angle arctan 2, and I can never remember, I think it's y and x. You know for sure? Okay, fine. All right, so we have these guys here. Now, presumably our, okay, we're going to need a few more parameters here. We're going to need a ring, sure, ring R. So that's the radius of the ring. and it's going to be specified in units of L over 2. Okay. And then we also, and I'm going to put L here. Yeah. Yeah, sure. Let's do L. You're going to have to specify the box size. And so this will be, let's say 0.5, I don't know, halfway at the center of the box. And then we need a ring thickness. What do you want to call that? Ring, sure, thickness. And I guess we'll do that as a function of L over 2 as well. Sound reasonable? Okay. The self ring R. Okay, so I'm going to set the parameters this way. Make sense? I'd guessed. Yes, at the end of the day, we probably will. Okay, maybe we don't want to do this. Maybe we want to do it in microns, because we're going to do everything in microns, right? Okay, fine. Fine. We'll just do it this way. Sorry. Okay, so the ring radius will be, so we have to have a default length, let's say 10. The initial ring radius will be 5. Where? Here? Sure. That's what you want? All right, fine. Then for our this phonon amplitude should be in terms of mu, actually, right? So we should multiply this by mu here. Yes. All right. Yep. Good point. Okay, so we have ring R. And we have ring thickness. What do we want a ring trap to be? Harmonic or Gaussian or what? So then thickness is not a very good. So maybe what we should do is we should do the ring. Sure. This will be thickness of the ring. This will be the trap length for harmonic ring potential. Okay. So this radial potential will be a harmonic ring. Okay. I think we have everything here. So now we have to go down here. We have to make our potential. So V ring is equal to R. Oh, so I guess I will need R. So we'll take the square root here. So it's R minus self dot ring R. Right? times 2. Okay, so what's omega ring? How is the trapping radius related to the frequency? What? No, it's just harmonic oscillator. Right, so we want the quantum harmonic oscillator. The harmonic oscillator length scale is there we go. Natural length and energy scales. Where is it? Yeah, square root of h over m omega. So omega is the length scale squared over h times m, right? So omega is going to be self dot ring times self dot m divided by self dot h bar. Well, it's a harmonic oscillator that's rotationally symmetric. Hang on. Ask your question in 30 seconds. So the length squared times m over h bar. Length squared, I forgot the squared. Where'd it go? Sorry, here we go. Length squared times m over h bar. And that's the square of the potential, right? No, that's actually omega. Okay, good. Okay, so then the actual frequency is omega, the trapping potential is omega ring squared times x squared, where x is the deviation of r from our ring. That's, I think, what you were saying, Ted. Divided by 2.0, and we need an m, right? Okay, so there's our ring potential squared. Thank you. I don't like that. Because we're using little r elsewhere, so. Okay, good. Okay. So now, oh, we made one other thing here is we have to go L, X, Y, Z. Okay, and we better put N in here as well. So N is 64 for now. So N, X, Y, Z is equal to N, comma, N. L, X, Y, Z is equal to L, comma, L. Okay. We could. We don't need to because they're being used here. What was it? N equals N. I don't want to do that actually because of particle number. I'm going to leave those. Okay. Now, so that's our ring potential. Okay. And now we want to put the phonon modulation on top of that. Right? And so we no longer want to have an over L. We no longer want to have a 2 pi. We simply want to have phonon kn times omega times theta. You don't need a 2 pi because theta goes from 0 to 2 pi. Right? So like that. Get rid of k and put it in like that. Sound good? Yeah, so that's the number of windings. And theta is the angular variable. So if it's 1, then it wraps around once, etc. And this trap is not a very good thing here. This is V phonon. What? L we don't use, actually. Oh, yes, right. So this will keep our trap. It'll keep the trap even if the time is greater than that, but it will let go of the phonon potential. Okay? Or maybe we can do this. Maybe we can say V ring plus equals. Okay? We don't want to turn the ring part off. We want to turn the phone. We only want to add the phonon thing if t is less than 0. Okay. Everything else is the same. Now we just turn this into L equals L. N equals 64. We'll still keep everything else the same. Winding. Now the winding we'll have to put that later. We'll do that later. This might be, since we need to do this, maybe it's useful to do a theta. We'll do this. Oh, the N disappeared. But okay, so we're going to need to put this a little bit later, but let's not do it now. Well, okay, we can do it now. So this is just, we're going to multiply it by e to the 1j times theta times winding, right? There. All right, let's see if this works. Self is not defined. Oh, right, this has to be state.theta. Okay, now here's something a little bit tricky. Cannot concatenate lists and float. I have no idea what's going wrong. So let's run the debugger. We're deep inside some contour thing, so let's go up. So we're trying to do a contour. X is that. Y is that. Okay. What's psi? I don't know what's wrong. Oh, looks like I have a bug in my contour plot program, doesn't it? Yeah, so this is my natural 2D plotting. Let's see what levels is. This actually is probably a change in matplotlib. Well, okay, so I'm going to have to change this function a little bit here. We could write our own plot function. This is kind of a nice plotting thing, but there's something a little wrong here. I'm just going to take a quick look and see if I can see what's wrong with this. Any questions? Oh, see, this is interesting. The levels are not being passed in properly. It should be a numpy array, and I'm not sure why. I'm not sure why C2 levels is not coming out properly. It's interesting, and I don't know why. So this would be a bug that you would file with MMF utils. For now, we're going to have to write our own plot function. So we'll just do that in the state. Okay, so how are we going to plot this? So we're going to get the x and y, right? And then let's just get the densities. And then we can go IM contour F, X, Y, and road. So let's just get that from MMF utils plot import IM contour F. See if that works. Oh, and I'm probably still running the debugger. So okay, so here we go. That doesn't look so good, does it? So let's plot instead. First, let's check the state. So let's check the maximum value. I'll have to get the actual array. Okay, so the state is actually 0. Okay. Yeah, we can't really do this at Webster here. Yeah, we could pop down there, I suppose. You want to do that? Okay. All right. What? All right, so we'll continue this at part 3. Well, let's finish the plotting, and then we'll continue the part 3. So, blah, blah, blah. Okay, so the problem here is that there's no density, right? Now, why is that? So let's get the potential. Let's take a look at our potential. So this is a contour plot of our potential. So that looks not too bad, right? Oh, that's rather large. Those are rather large values, though, aren't they? Is that what you were trying to say? I think this is to do with how we're specifying the thickness of the trap. We're making the trap, the harmonic length, 1 micron, and that's kind of crazy. Yeah, we need more than that. So let's just try quickly with, let's try 100 microns. Let's do that. So that's 10 to the 14. Oh, there's something wrong. There's something wrong. The trap radius should be, they should be inversely proportional. So it should be, omega should be h bar squared over m, h over m r squared. Yeah. So it should be, yeah, self dot h bar divided by self dot m divided by ring thickness squared. There we go. Yeah, that looks better. Okay, so let's stop this and we will continue this in Webster on part 3.